Hi, my name is Brian Caffo, and welcome to this week's Ask Brian, part of our weekly newsletter. Our weekly newsletter, Monday Morning Data Science, there's a link in the video description below that you can click on. There's a link there also to ask a question. And then also, if you get a chance, subscribe to the YouTube channel. Okay, so last week I talked about what was a generalized estimating equation. This week I'm going to talk about what is a generalized additive model, or GAM. Okay. So obviously this is kind of a big topic. So I'm going to get through as much as I can in 5 minutes that I have here as a big overview. Okay, so before I cover GAMs, I have to talk a little bit about scatterplot smoothing. So imagine you have a picture like this right here, where we have a y and an x, we want to fit a nonlinear function through it. So we might think of a model like this right here: y is equal to f of x plus an error term. Well, fitting this function without any further structure would be very hard. So one way we do this is we create a broad class of functions that are characterized by building blocks. And one convenient way to do this is to just think of the building blocks as a basis. And these bases get added up plus coefficients to form the function, and the collection of functions that can be created by such bases are often quite large. So an example basis would be the polynomial basis, 1x, x squared, x cubed. And you can see how you could then fit a nonlinear function with just regression. You would put in an intercept, you put in the x variable, you put in the x variable squared, you put in the x variable cubed, and so on, and then you fit a nonlinear function. It turns out that that kind of Taylor approximation doesn't work very well, except at where the Taylor approximation is centered at. Okay, there's other bases like Fourier, where you do sines and cosines of the x's, and then wavelet, where you do a wavelet basis, and these all have different properties. Another kind of basis are the sort of regression spline bases like this. They look like that. That's what the functions look like. And they really boil down to this kind of function here, where the function is something like x minus the naught point plus is the notation. And that's 0 for x less than or equal to the naught point. And it's x minus v for x greater than the naught point, where the naught point is that point right there. Okay, so if you were to do this to this scatter plot over here, you would get a continuous function fitting it. The f that you estimated would be continuous, but it would be a little bit like a broken stick at places, right? It would be continuous, but it would have like really hard turns in it everywhere there was a naught point. You can avoid that by squaring that and including a 1 and x squared polynomial terms in the fit, and then you get something that it has a continuous derivative at all the naught points, so it's nice and smooth. Okay, so you could see it wouldn't be very hard to go from that way of thinking, right, to fitting a nonlinear function via scatterplot smoothing, to also including other covariates in the fit. And that's what a generalized additive model is. It might have one or more nonlinear functions, but then it also has potentially has other covariates in the fit. And then, you could also have instances where, for example, for a treated group, you have one nonlinear function, and for a control group, you have another nonlinear function. And, if you're just doing regression splines, you could do this all in the context of least squares. Okay. If you have Poisson or count data or binomial data, you might then instead do this in the linear predictor. Okay. So that's where we get the generalized additive models would be the same thing as a general linear model, but then with a nonlinear function as part of the linear predictor. Okay, so the original work on this by Hastie and Tibshirani, part of the innovation was the algorithm for fitting really nice kind of complicated smoothing algorithms to the nonlinear functions, because regression splines have some problems. As an example, you got to figure out where to put the knots. You got to figure out how many knots to put in. You got to figure out the order of the basis, that sort of thing. So they had a way to kind of by iteratively sort of fitting residuals, that sort of thing, and using regular smoothers, they had a fast way to fit these kinds of generalized additive models. Since then, there's been a bit of a revolution where the thinking now is to treat these parameters as if they're random effects and penalize them with a normal distribution on them. This has several benefits. One is, for these kinds of regression spline type bases and other related bases, it doesn't matter how many knots you put in, as long as you put in enough, they tend to work well. The other interesting fact is you can estimate the kind of degree of the smoother using maximum likelihood or restricted maximum likelihood by estimating that variance component. So it gets rid of the need to doing something like cross-validation to figure out how smooth to make the smoother. So this modern approach to GAMs uses mixed models. Okay, so to summarize, what a GAM is it's a way to put a nonlinear function into a generalized linear model, one or more nonlinear functions into a generalized linear model. This is usually done by taking the function, turning it into building blocks, and then fitting the smoother via some strategy. And again, I would say the modern strategy I would recommend involves mixed models, and I would look up the program in R, MGCV as a modern that has a lot of different ways to do this, but includes some of the mixed model smoothing. Okay, well, hopefully that answers you a little bit, and I'll put some links in the video description that will help you get some further reading on this, but hopefully this gives you some of the basics. All right, well, I will see you next week, and remember to keep asking those questions.